So, Chapter 5, Discrete Random Variables. We're going to talk today about Section 5.2, the mean and the standard deviation of the discrete random variable. To get started on that, we're going to take a look at this Carnival Game. It costs $1 to play this game, and in this game you draw one card at random from a deck of 52 playing cards. If you pull out the ace of spades, I pay you $10. If you pull out any other ace, I pay you $5. Let's get this off here. If you pull out any other spade, I give you $2. The question is, well, would you play this game? Is it a fair game? Now, just a big discussion can cut here on what do we mean by a fair game. But let's see what happens if we run this game and play it a little bit. Now, I tried doing this where I would... we're going to go over here. This random.org, we use this site when we did our probability lab. You come under games, you can pick a playing card shuffler, which is what I'm using here. This is going to draw one card at random from a deck of 52 cards. I tried doing it so that I could run the simulator and keep track of everything on screen. We can watch it as we go by, and it turned out just a little clunky. So I'm gonna write this down. You might want to jot it down as we go through it, and then we'll analyze this to see what we can find here. We're going to run 20 times. So let's start. 6 of clubs, nothing. 3 of hearts, nothing. Queen of spades, a spade, $2, a winner. We got another winner, $2. Woohoo! Nothing. 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 Looking good for me, huh? Nothing. Woo. There's another spade. There's $2. Nothing. Nothing. Another spade. No big payoffs so far. Another spade. Okay. Just to keep people interested. Oh, another spade here. Nothing here. And nothing there. So there's my 20 rolls. So let's see what happened. I got 0, 0, 0, 0. Whoop. Sorry. 0, 0. And I got a couple spades. 2, 2. 0. So after the first 5 players, I'm $1 up. I got 0, 0, 0, 0, 2. After 10 players, I'm $4 up. 0, 0, 2, 0, 0. 15, I'm $6 up. 0, 2, 2, 0, 0. So after my 20 players, I've collected $20. I've paid out $12. I have a profit of $8. That's looking pretty good. But what if somebody in there got a spade, or the ace of spades? We throw out a 10. Out of 20 players, I paid out $22. I'm down $2. So, back and forth here. This is kind of what's going on. Unless we hit one of those big cards, it looks good for me. But if one of those big cards gets hit, then I'm paying out the money and I'm behind there. So is it a fair game? That's kind of what we're going to look at in this lesson. So, our learning targets are we're going to calculate what we call the mean of a discrete random variable and the standard deviation of a discrete random variable. These are kind of the tools we will use to look at something like this and say, is this fair or not? So, let's start with the mean. when we talked about the mean was just the number of times something occurs. We sum up all the x's. Sorry, I'm talking about something else. I'm talking about probability. The mean is just you sum up all the values, divide by how many there are. This is talking about a variable of finite populations. We can use this with discrete variables, with probability and with discrete variables, because again, we have discrete things we can add up. As I ran that program, that game 20 times, I can add up all my results. I do have a finite population here. I need to quit messing with the mouse here. So we're going to look at another set of data with this here. Looking at my niece's wedding, she had eight couples in her bridal party. And she had mostly, people her own age in there, but she had one older one in there. So this was the ages of the 8 groomsmen. So why does this keep popping up here? I don't want that to pop up. This is annoying. So what we're going to do is take a look at this data and make a probability distribution and explore the mean age. And it keeps popping up. It just hates me. I don't know. So, to find the ages, what we're just going to do is add up all the ages, divide by how many there are. Right? So we got 19, 19, 20, 20, 20, 21, 21, 27. So let's kind of group this together. I got 2 19s, so I can just go 19 times 2. 3 20s, 2 21. So instead of adding all of those, I'm going to make my adding a little easier, right? Okay. Well, if I have it written like this, since I'm all dividing by just everything's divided by 8, I can break this up into 4 different things. Divide each by 8. So I'll take 19 times 2 over 8, 20 times 3 over 8, 21 times 2 over 8, 27 times 1 over 8. So I can do that since I'm just dividing by one number. I can divide each part of that I'm adding, and when I take 19 times 2 divided by 8, I can just do the 19 times 2. I can do that, messing things around with that. But look at those numbers: 2 over 8, 3 over 8, 2 over 8, 1 over 8. Those are your probabilities. So I'm taking 19 times the probability that x equals 19. 20 times the probability that x equals 20. In other words, I'm just adding up the value times the probability that x equals that value. So we can find the mean just by using the probability distribution. We don't have to have all the data. We just need to have the probabilities. And based on the probabilities, we can find the mean. So, the mean of a discrete random variable x, we're going to use mu because mu is our population mean. We're going to put x as a subscript to say it is the mean of the random variable x. And if we have no confusion, no other things going on, there's only one mean we can talk about, we'll just call it mu. But we'll sometimes put that x on there to say, yeah, this is the mean of a random variable x. We call this often the expected value or the expectation, sometimes instead of the mean. Again, we're just going to do that. The adding up the value times the probability that you're going to get that value. So, if we look at our Carnival game, and let's apply this formula to it, we can figure out what the probability of each of those payoffs are because of based on the deck of cards. Now, since we need our probability distribution, we need to add it up it add up to 1, the probabilities, I need to add in the payout of 0. I get a 0 payout 36 out of 52 times. So I have those different probabilities and all the possible payoffs. My possible payoffs are 0, 2, 5, and 10. So when I work this out, I take 0 times 36 over 52. I take 2 times 12 over 52. 5 times 3 over 52. And 10 times 1 over 52. I get those those values, add them together, I get 94 cents. So with this game, okay, the mean value was 94 cents. What it means is the expected value, or if I play this enough times, every time I'm going to pay off, on average, pay off 94 cents. But each time I'm getting paid $1 to pay out 94 cents. So on average, the expectation for the player is I'm going to lose 6 cents every time I play the game. Now, you never actually lose 6 cents. You either get a bunch of money or you get nothing, which means you lost your buck. But you flip around on my side as the person running the game, I can just say pretty much I can expect to make 6 cents every time somebody plays the game. Every once in a while I have a big payoff, and yeah, I got to pay off a bunch of money, but enough people are going to get nothing that it's going to average out, and that mean value is going to be 6 cents. Okay, and we talked about, when we looked at that probability again, that probability lab talked about the law of large numbers that says if you run it a large number of times, you will... Sorry, I lost my train of thought. Large number of times, you will hit that mean value. But if you're doing it in the short run, no, you're not going to. So that's why, when we ran it only 20 times, we had nothing close to that, because I made a lot more money than 6 cents per time. But I didn't do it a large number of times. So that's kind of how those carnival games, you talk about casinos, you talk about any place where you're, spending money to try to make money by pure chance. That's what they mean by the odds are in favor of the house, that on average, the person running the game is going to make money. Even if there's a big payoff now and then. And so once in a while you get people that make it big, and a lot of people don't. Right? So, standard deviation, I'm not going to go through and derive these formulas for you. The standard deviation, which is sigma of x, we can calculate it by doing the sum of x minus mu squared times the probability of x equals x. When we look at this, we're actually taking the sum of this whole thing. So for each x value, you say x minus mu squared times the probability of x equals x. Then we go to the next, x minus mu squared. So we're not taking this sum and multiplying by one probability. You're multiplying by a probability each time. So that's kind of to get straight on this formula. But on this one, the computing formula, you're just going to take x squared times the probability of x equals x. Sum all those up, and then subtract mu squared. And then we take the square root to get my sigma. So let's actually do those. So with my carnival game, here's my x minus mu. So basically, this is, my 0 minus 94 cents, 2 minus 94. I square that number. I multiply it by the probability. That's what I add together. I take the square root of that number, and I get my 1.844 once my little thing chills. That's using that defining formula. If we do this with the computing formula, we just take my x squared, 0, 4, 25, 100, times the probability, add them up together. So notice here, we added, oops, go back. We added all these together first, and then we subtracted the mu squared and took the square root of that to get my standard deviation of 1.845. Now, I'm off by 1/10 of a cent, and that's due to rounding problems in there. So that's still not too bad. If we look at this, the average payoff varies from the mean by $1.84. That's quite a lot. But one of the things you got to remember, standard deviation and mean are not resistant. That $10 outlier has a large effect. It's not going to have too much, or not going to happen too often, but when it does, it can really skew things up. And that's kind of what, truth of the matter, in those games, you throw in that one big payoff to try to get people in to play the game, thinking, yeah, I know I'm probably going to win, but just think what happens if I win that big time. But that's enough to get enough people to play that you're still going to make the money off of it. So that is mean and standard deviation. So here's your assignment. Give that a try.